Chapter 2, Circuit Elements. In this lecture, we will first define a node and describe the behavior of current at a node to help us understand the importance of nodes. Next, we will define Kirchhoffs Current Law and perform some example problems demonstrating nodes and how to use Kirchhoffs Current Law to analyze simple circuits. We are looking at objective number 2, which is to be able to state Kirchhoff's current law and be able to use this law to analyze simple circuits. A node is a point where two or more circuit elements meet. Let's look at an example with three basic circuit elements. Our node would be right here. Notice that we have current in the direction into the node and the direction leaving the node. Let's take a pen and draw this. So in this circuit element, the current is entering the node. In this circuit element, current is also entering the node. But in this circuit element, the current direction is leaving the node. Let's look at another example. In this example, we have a node at A, we have a node at B, we have a node at C, and we have a node at D. If we look at node A, the current from the source is defined as leaving node A, but from the circuit element R sub 1, it's entering node A. At B, I sub 1 is leaving node B, and I sub C is also leaving node B. At C, node C, by definition, our current I sub C is entering node C, and our current I sub L is also entering C. If we look at node D, the current I sub S is entering node D, and the current I sub L is leaving node D. So current is like a river. If you have a river with two branches, the water in the river will split between those two branches, and it'll run down both branches. If you have two branches entering one, same deal. Let's change the color here. The current will flow in one branch and the other branch, and they'll both be flowing in the main branch. All right, let's do some more examples of nodes, finding nodes. In this one, we have a node between the voltage source and the 4 ohm resistor. We have a node where the terminal from the 4 ohm resistor, a terminal from the 3 ohm resistor, and a terminal from the 18 ohm resistor all meet. We have a node where a terminal from the 3 ohm resistor and a terminal from the 6 ohm resistor meet. And we have a node where the 120 volt voltage source terminal meets, a terminal from the 18 ohm resistor meets there, and a terminal from the 6 ohm resistor meets there. So let's take a look at the bottom node, and let's look at the current that's entering or exiting this node. The voltage source has a current that's going in this direction, so it is leaving the bottom node. The 18 ohm resistor has a current that's entering this bottom node. And the 6 ohm resistor has a current that is also entering the bottom node. So the bottom node has 2 currents entering and 1 current leaving the node. All right, let's look at this circuit. We have a node at A, we have a node at B, and let's just take a look at this. At A, we have this circuit element, this 2 ohm resistor element, 4 ohm resistor element, and a 5 ohm resistor element. They all meet up at A. B has the 1 ohm, the terminal from the 1 ohm resistor, a terminal from the 2 ohm resistor, a terminal from this current source, I sub A, a terminal from 3 ohm resistor, and a terminal from the current source, I sub B, all entering at the, or all intersecting at node B. Then we have node C, node D, but what about this one? If you look at this, this wire is not needed here, and we could just scooch C over here. Same with D. We could scooch D over here. So what we have is one very large node that's kind of a weird shape. And you'll notice this node has a current exiting and the same current entering that very same node. Okay, let's move on to another example. In this example, we have a current source, a resistor, another resistor, and the 4K ohm resistor, and they all have terminals that meet here. And this 4K ohm resistor, 20K ohm resistor, and 2K ohm resistor all have terminals that intersect here. And this 2K ohm resistor and 3K ohm resistor all have terminals that intersect here. And lastly, this 3K resistor has a terminal, the terminal from this 20K resistor, the terminal from this 24K resistor, this terminal from the 6K ohm resistor, and this terminal from the 50 milliamp current source all meet at this bottom node. Ohm's law gives us a relationship between voltage, current, and resistance at each of these nodes. So if we're looking for a current or voltage, we could potentially find it, but we may have multiple unknowns, multiple currents or multiple voltages that we need to find to solve the circuit. And as you know, to find n unknown quantities requires n simultaneous independent equations. So applying Ohm's law to circuit elements to find these quantities, these unknown quantities, could be helpful, but Kirchhoff's current laws and Kirchhoff's voltage law allow us additional constraints to define voltage or current, or to solve for voltage or current in a circuit. You will see Kirchhoff's current law or voltage law abbreviated as KCL or KVL. We are going to be looking at Kirchhoff's current law for this lecture. And Kirchhoff's current law states that the algebraic sum of all the currents at any node in a circuit equals 0. So here we have a node, and we have 5 currents entering that node. I1 is entering the node, I2 is entering the node, I3 is entering the node, I4 is entering the node, and I5 is entering this node. So if we were to add all of these up according to Kirchhoff's current law, adding them up, the sum would be 0. Now, as you know, we could have a node with currents entering and currents leaving the node. So we have to assign a positive sign to the current or a negative sign. Now we have to choose. And the standard is to choose a positive sign for currents entering the node and a negative sign for currents leaving the node. So that would give us the KCL equation for this node would be I sub 1 plus I sub 2 plus I sub 3 plus I sub 4 plus I sub 5 is equal to 0. For our second node, it would be I sub 1 plus I sub 2 plus minus I sub 3 plus I sub 4 plus minus I sub 5 is equal to 0. Now we can restate Kirchhoff's current law, and instead of saying the sum of the voltages, or the currents entering a node is 0, we could say the algebraic sum of the currents entering a node is equal to the algebraic sum of all currents leaving a node. So let's take a look at the previous two nodes. Actually, we're just going to look at this one node, which has currents entering and currents leaving. So this one could be written algebraically as the sum of all currents entering the node is equal to 0. Or it could be written as the sum of the currents into the node is equal to the sum of the currents leaving the node. So into the node we have I sub 1 plus I sub 2 plus I sub 4, and leaving the node we have I sub 3 plus I sub 5. Now you'll notice I sub 3 and I sub 5 are written as positive numbers. So both leaving the node and entering the node are written as positive numbers. Whereas when you do it this way, you have to change. Either leaving the node will be positive and entering the node will be negative, or entering the node, which is the standard, is positive and leaving the node is negative. Okay, click on the link below to view the video of this example problem using Kirchhoff's current law. All right, in review, in this lecture we defined a node. We located nodes in several circuit examples. We then defined Kirchhoff's current law and performed an example problem using Kirchhoff's current law. And that concludes this lecture.